nothing better than having some IT problems to start with, but that shouldn't hold us back from anything here. Welcome. What's happening right now in data science for cybersecurity is a little concerning, and in some cases, even dangerous. We're giving our attackers the overhand in some cases, which is not really what we want to do. We're going to explore in the next 50 minutes the topic of artificial intelligence and machine learning a little bit, and talk about why algorithms can be dangerous. We're going to explore a number of topics during the talk. First of all, we're going to look at why we don't have artificial intelligence yet. Algorithms are getting smarter, but experts are more important than the algorithms. Stop throwing algorithms on the wall. They're not spaghetti. We don't have to just throw something on the wall to see what sticks and see if we can find anomalies. I can take any algorithm, find something interesting in your data set. But understanding what we're finding and what the white space is around it is very important. Understand your data. I say that again. Understand your data and your algorithms before you do anything with it. Invest in people who know security. Hire good experts if you can find them. And all of you probably qualify for that. Build systems that absorb expert knowledge. Don't just run an algorithm that randomly throws something up, but figure out how to put expert knowledge into these systems. Think out of the box. History is really bad for innovation in a lot of cases. I love the delay on this thing. My name is Raphael Marti. I've spent the last 20 years in cybersecurity looking at data and how we can apply interesting algorithms to the data to find insights. I started back in the day at IBM Research, where we did a lot of anomaly detection research on firewall data and intrusion detection data. I then moved on to ArcSight, where I started the solution and content teams, where we continued some of that work on how do we make that data actionable. I went over to Splunk, continued the work, and sort of helped Splunk setting foot in the security market. How can we solve the security use cases? I started a couple big data companies where we applied data science and big data to the security problems. And currently, I'm running corporate strategy at ForcePoint, where we're focusing on understanding the behavior of identities, of users, of devices, to see what's anomalous. And we are trying to understand how the data moves around in your network to also find when something is going bad. We're doing this across our portfolio of products on firewalls, DLP, and CASB, and Insider Threat, and so on. We call this whole thing the human point system. I'm going to look at three areas in this talk. First, we're going to look at a brief definition of what machine learning and artificial intelligence really is. We're going to look at the dangers of algorithms and why just applying some of these algorithms can actually be very dangerous. And then we're going to step through an example together. So starting with some brief definitions, I don't want to bore you with these things. These are not academic definitions, but I want to have some kind of a working definition for this stuff. When we talk about machine learning, there we go. Machine learning is sort of a way, an algorithmic way to describe data if you want. There's two subcategories that you might have heard of. There's supervised, and then there's unsupervised machine learning. In the supervised case, we're basically giving a system a lot of training data where we already know the outcome of what it is, if it's good or bad, or if we classify it in a certain way. And the system learns the characteristics of those data sets. In the unsupervised case, we are kind of giving the system some kind of optimization to solve. Think of clustering, for example, where we're trying to extract the inherent we're trying to extract the inherent structure of the data to see how the data is sort of made up of. And I have a couple examples in a second where we're going to visualize some of these and get a little better feeling for this. What you probably have heard of also is deep learning. Everybody talks about deep learning as the solution to all of our problems, right? It's going to help us with all kinds of different things, and it's also the promise is that it should solve a whole lot of security problems for us. Well, it actually has helped us in a lot of areas of security to advance incredibly. I will show you some examples of that. But in the end, deep learning is nothing else than a little more sophisticated machine learning algorithm. It's not that much newer than what we had before. It has a couple of very interesting advantages. One, it eliminates sort of the feature engineering step. What that means is when you're taking the data and you put it into the algorithm, you have to sort of extract certain characteristics from the data that you feed into the algorithm, and that step can be eliminated in certain cases. One big problem, though, with machine learning is that it has an explainability problem. What that means is I can't look into that black box. I basically put data in, this box learns something and outputs something. I can't look into there to explain what it just learned. And in a lot of cases, that's very concerning to me, right? Do I really trust a black box to make the right decision on all kinds of different areas? Then we have data mining. Data mining is basically a way to explore data. Data visualization is often put into the data mining environment, and I'm going to show you a couple of visualizations. And then we have the great topic of artificial intelligence. We do not have artificial general intelligence yet, like what we would think of as an intelligent system that just learns something and comes up with new knowledge. We don't have it in any field. We have smart algorithms. I was trying to define at some point how would I define that for cybersecurity to have real artificial intelligence? And what I came up is I said, you know what? If it's a program that doesn't simply classify or compute model parameters, sort of taking out the machine learning cases, but it actually comes up with novel knowledge, something that I haven't known yet before, that a security expert finds interesting. Right? It needs to apply somehow. It can't just be any novel knowledge. It's like, oh, duh, yeah, okay. It needs to be sort of security relevant. And we really don't have anything like that yet. Whatever the vendors are claiming in their marketing, they probably refer to analytics as artificial intelligence, right? Colloquially, people use artificial intelligence to mean analytics. And that's also, I'm going to probably in my talk say artificial intelligence a couple of times, but what I really mean is analytics. Where are we today with artificial intelligence in general? We've all heard and seen a bunch of smart algorithms that solve certain problems, right? It got really, really good at certain games. We have now computers that are way better than people at playing chess, right? Deep Blue being the example there. Then we had AlphaGo from Google that beat the Go world champion. Go is an incredibly complex game. It was very complicated to build that system. We have in drug discovery, there's a lot of artificial intelligence or advanced analytics being used. And then obviously, you all have used some kind of speech recognition, be that Siri or something, where artificial intelligence or this kind of analytics really has made a difference. Now, if we look in security, where we had, or where we are using machine learning, I was trying to inventory a little bit, where are we using supervised and unsupervised machine learning today, and where it's actually working. And I didn't find that many examples, actually. There's definitely, when we talk about malware classification or binary classification into malware and goodware, there's immense advances we have made in cybersecurity and in that whole field. There was a talk earlier today by Josh Sachs from Sophos who was talking about deep learning, and he is explaining sort of how we really made incredible leaps in detecting malware better today with deep learning than we were able to do that ever before. In spam identification, we have made great advances. And then there's a very interesting project, MLSec from Alex Pinto, where they looked at firewall data to understand where there are bad areas in the internet, bad IP spaces. On the unsupervised side, there's all kinds of interesting examples. There's DNS analytics, obviously on threat intelligence, when you're trying to deduplicate things, when you're trying to prioritize IOC feeds and things like that. There's some very interesting work that we want to get into a little bit in the end on sort of the tier 1 analyst automation, so that the whole triage in your SOC, for example, there's some very interesting stuff going on there. All right, so that's a little bit of ML and AI in a very short terms. Let's look at why it is actually kind of dangerous to apply some of these algorithms. So this is, if you're looking out there in the news and the literature, you find a lot of examples where artificial intelligence has failed or has produced some not so good examples or good outcomes. This is stuff that you find on the internet when you Google this. You can read those yourself. One example was pretty interesting. The Department of Defense had a project where they were trying to take images and understand whether there was a tank in the image or whether it was just a field. And the tanks were often sort of camouflaged. It was not that easy to find them. So they took a whole bunch. They took like 100 images to train this system and to understand whether there's a tanky there or not. And then they applied it in the field, and the system did horrible. Because what happened is they noticed that all the images they fed the system that had a tank in it were taken in cloudy environments. So it was kind of a dark picture. And all the images where there was no tank in it, was just an open field, were taken in sunshine, so the picture was much brighter. So the algorithm basically just learned the brightness of the image to classify whether there's a tank in there or not. And that was obviously quite a fun failure. So this is sort of the money slide. Why is it dangerous to just apply algorithms to your data and try to find attackers or bad things in there? There's a number of things. To start with, it's the data itself. The algorithms often make assumptions about the data. We need to have clean data first. Who in here has looked at net flow data ever in their lives? Whoa, I'm sorry for you guys. There's a bunch of stuff in there that you will find that's kind of tricky to clean up. Often the source and the destination are going to be turned around in your records. You have to clean that up. I'll show you a visualization in a second where that wasn't done. A lot of people don't even know that, and they just do some analysis, and you get all kinds of wrong results doing that. Often the algorithms, they assume a certain type of data. Normally distributed data, for example, categorical data versus numerical data. We have to be aware of that to understand how to apply the algorithm to the data. Often the algorithms don't deal well with outliers, so often we have to eliminate them first because they're really going to skew our data. Machine learning assumes enough, especially supervised, assumes enough training data that we can actually train the system well enough, right? That's in statistics, you learn that. What's the sample size you have to take to make it relevant, right? Often we need context to data. Just an IP address often doesn't tell me much. I want to know the host name or the role of the machine, things like that. We have to augment our data. And then there's even more technical, right? The algorithms, they often, or pretty much all the time, require that all the data is normalized in the same way. So if you scale something, you have to scale all the inputs, because otherwise one is going to dominate it. So that's on the data side. There's all kinds of bias in the data. It's also what data sets are you choosing to train your system. Do you have a historic data set? Well, where did you get it from? Does it really have all the artifacts in there that you're trying to train the system on? How do you know? It's way too easy today to run a machine learning algorithm on your data. You can go online, download TensorFlow or Torch or something, run that on your data, and you get an output and says, look, here's all your anomalies. But do you know what the algorithm did? Do you know that there are parameters in there that you might have to tweak? That if you don't change them, you might get completely wrong results. And there's too many people doing that, and I'll show you an example of how that looks in the end. And then algorithms don't know anything about your domain. They don't know about security. They don't know that the layer 4 protocols are all slightly behaving differently, and you probably want to train each individual protocol on its own because they have very different characteristics. How do you define meaningful distance functions when you're doing clustering? I'm talking about it in a second. Again, I'll show you an example. And then one of the things that drives me absolutely nuts is when people are using port numbers as integers. They're saying, well, 80 is 1 away from 81, 2 away from 82, so they're very close together. And then 443 is really far away, right, encrypted HTTP. And then 8080, which is often proxying, is even further away. They're all almost right next to each other, right? They're closer together than 80 and 81. So you have to take that into account. It's not a numerical value anymore that you can just plug into an algorithm. And that gives you some really strange results. If you're looking at the data and the biases in your data, there's a bunch of other things. I have an interesting example here where if you go to Google Translate and translate this very simple sentence here into Hungarian and then back from Hungarian into English, there is a bias in here. It starts with, he is a nurse, she's a doctor. If you translate it back, you get exactly the other gender back, right? She is a nurse and he is a doctor. So there's all kinds of bias in our algorithms, in our systems that we don't even know about, right? If we just translated that when we didn't know where it actually was translated from, we wouldn't know what's going on. Again, it matters a lot on what the data set is that you're using to train these systems. Where do you take it from? Do you have enough historic data? Do you have everything covered you need to know? Are there collection errors in there? How do you know? There might be missing data, right? Maybe you have a misconfiguration somewhere where one host doesn't generate certain event IDs. And you're still learning on that data set, and suddenly this machine is really skewing your results. What's the context you operated this whole thing in, right? And if you're taking it from one customer environment to another, what are the differences there? Are they homogeneous? Are they the same? Do I have to take that into account? How do I take that into account? Another example, FTP, right, is generally not considered, or is generally considered insecure. And often you would say, you shouldn't use FTP anymore. That's old and not encrypted, and that's a policy violation. It's bad. In certain environments, it's absolutely needed. We still have mainframes where every day we're downloading FTP to get data and transactions onto other systems, and there's just no other way to do it right now, right? It's not an anomaly there. It's actually normal to use that. And then, finally, how do you know whether you can trust some of your data inputs? Intrusion detection systems, right? How do you know the confidence you can have in a certain event that's generated? How do you know it's not a false positive? There's a very interesting example that I show. I used to teach a class here at Black in the last few years on data analytics and data visualization. I would show this visualization between two nodes. It had sort of two events generated between two machines. One was a UDP bomb, and the other one was some IKE, some alert that came up. And I was asking the students, what's going on here? And they're like, oh, there's like a DDoS attack over UDP happening, right? This UDP bomb thing, and then there's an IKE key exchange going on. And I'm like, well, I can read too, right? Like, that's just like seeing what's written there. But really what's happening, it's just a VPN login. There's an IKE exchange, there's a lot of UDP traffic happening. The IDS has a certain threshold set that if it sees a certain amount of UDP, it calls it a UDP bomb. So you have to interpret these things in the right way. You can't just read them off and believe in it. And that's where you need the domain knowledge. I tried to put together a couple of facts or a couple of sort of guidelines on when you should not be using machine learning for your data. If you look at a very simple sort of data flow, right? You have data on the top left, you put that into this machine learning black box, and then out comes some kind of detection, some classification, some output from this algorithm. Often you also add expert knowledge into the machine learning algorithm, right? You want to teach the system what features to extract exactly, or how to interpret certain things. Now, don't use machine learning if you don't have enough quality labeled data, right? If you don't have enough test data, don't use machine learning or supervised machine learning. Make sure your data is clean. It's normalized in the right way. Look at your timestamps. Do you have time zones in there? Make sure you account for that, right? When you're collecting from different parts of the world. These things happen at different times, even though they say the same thing if they're in different time zones. Make sure that you have enough understanding of the data to engineer meaningful features. If you're using deep learning to classify files into malware and goodware, or benignware, whatever you call those, if you just take the byte stream, like you took an image to do image classification with deep learning, if you just take the byte stream, that thing is just going to learn individual byte features. But a file, there is a reason why 2 bytes are next to each other, or 3 bytes, or 4. You have to take n-grams in there and feed into the algorithm, right? You can't just blindly take individual bytes. So you have to know that actually matters. Maybe you want to engineer other features and say, oh, there's a data segment, and there's a code segment, and there's all these other things in there that you can use as very high signal features for your algorithm. And that's where you need the domain knowledge. And then make sure that your data is not prone to adversarial input. So that someone couldn't cheat or inject false data or misleading data somehow into your algorithm. In the middle side, make sure that you have well-trained domain experts. Send them to the classes here. Send them to other classes. Make sure that you're exchanging knowledge with your peers. If you're in the financial industry, I don't think you're going to get a huge competitive advantage by having a little more knowledge on the security side than your other financial service. Talk to each other, right? And there's all these FSISACs, like the Financial Services Information Sharing Group. There's for all kinds of different areas, for retail, for automotive. There's these interest groups. Participate there. Talk to each other. Help each other out. We're one community, right? Help each other out doing these kinds of things. And then make sure that you have someone, data scientists that understand security. So you need to find these unicorns out there that understand both domains, security and data science. Believe me, it's incredibly hard to find those, and those who've tried to hire these people, it's not easy. But we need people that understand both, or at least put teams together that had both sort of domains together, where you have the statisticians, data scientists that really know the data, or the algorithms and statistics, and then you have the domain experts that can help putting the expert knowledge in there. If you want to really make sure that you can verify your output and you can interpret what the system learned, machine learning might not be the right thing, because we have this black box. If you're doing deep learning, in the end what you end up with is a bunch of nodes and weights on those nodes. What's the knowledge that this thing learned? I don't know. There's just some numbers in there, right? I can't extract the knowledge of what it actually learned. I can't extract the rule. There's a lot of research going on right now and people trying to figure out how do we solve that problem. But I'll show you a different approach that sort of circumvents that to start with. So here's a very quick example. I stole this from a paper that I found where machine learning is pretty prone to adversarial input, right? On the left-hand side, what you see is the regular image of this panda. The algorithm looked at it and said, with about a 60% confidence, this is a panda. It's pretty okay, right? But at least we identified the panda. Then, these researchers were adding some random noise. The image on the right contains that noise. The human eye, we can't see that. At least I can't. It's still a panda. But now the algorithm is absolutely sure this is a gibbon, right? There's no doubt. It's like 99.3% confidence. So these are the problems that we're dealing with. Imagine this is a stop sign in an autonomous car. It's trying to read that stop sign. Okay. Give you a little bit of an overview of what's machine learning, artificial intelligence, the dangers of the algorithms. Let's go through an example and kind of drive some of these points home. The task I'm going to give you, or we're going to solve together, is we're going to look at network communications. We're going to take some net flows, right? For those who have done that before, we're going to find this familiar territory here. And what we're going to do is very simple. We're going to try to find anomalies or attacks in here. Okay? How do we do that? Well, deep learning, everybody says this thing is solving all of our problems. Why don't we try that? Supervised machine learning. Well, deep learning has a few very interesting promises. It does the auto feature extraction thing, right? We don't have to do crazy feature engineering. It promises us. It has a pretty high accuracy for detection in general. So that's all great things. Okay, do we have all the right requirements met? Do we have a lot of data? We do, right? We can collect a lot on net flow. I can send you tons of net flow if you want some. But here's some caveats. A single record in a net flow is just a session between two machines. That doesn't necessarily tell me enough whether this is good or bad. Right? Someone connecting to a website, that could be good or bad. So I don't have enough context in a single record. Well, what we could do is we probably could do some pre-processing where we put certain sessions together and extract some interesting features. Possibly, right? We can still work around that. We probably don't have enough information in these flows. We just have IP addresses. We don't know what these machines are. And without that context, it's pretty hard to say whether something is anomalous. If I know that this server is a DNS server and it serves up websites, it's probably not very smart. I often don't co-locate my DNS and HTTP or web servers, right? So if I know that, I can make a lot better statements. We could import some context, right? We could add some information from our asset management systems and augment that kind of information. Can still do that. Now, the big problem is we don't have labeled data. We don't have a training set where we know for these records, they're good, and these records, it's bad. People have tried all kinds of things. There's all kinds of synthetic data sets out there that people have been trying to build for years and years and years. Every single data set, at some point, some researcher came along and said, oh, you know what? You can do all kinds of crazy learning on this data and come up with very complicated rules and things like that. But guess what? If you look at the TTL, if it's below 20, it's an attack. If it's above 20, it's normal. So they found one artifact in the data that's giving it away. So building the perfect data set is almost impossible. And how do you build a data set that's sort of generic enough to cover all the different scenarios that you want to have it run in production in the end. Okay, so I guess deep learning is not the answer for everything. Well, maybe unsupervised learning is going to be helpful. Basically what we want to do is we want to exploit sort of the inherent structure in the data to find anomalies in attacks, right? So something like on the right-hand side, where I take this data and it creates these squiggly lines and I see, oh, this is normal and this is abnormal. How would we do that? Well, here's just a little process that we're going to walk through quickly. We got to clean the data. We're going to engineer the distance functions. We're going to figure out the right algorithm. There's multiple clustering algorithms out there. We got to apply the right parameters to the algorithm. I'll show you what happens if you don't. And then we have to interpret the data. So let's get into that. This here is a visualization. It's called a parallel coordinate, where you see every vertical line in here is one field in your data. So the first part there is the source IP address. Then the second is the time. Then you have the source port. Source port starts from 0 on top, going down to 65,535. Then you have your destination port. And one event, so one flow, is one line going from left to right. Right? So it starts with some IP, some port, or at certain time, port. So you have one line is one record. Here's a bunch of records visualized. Now this is from a challenge. The VAST community, the visual analytics community, puts out a challenge every year. And for a number of years, they put out network flows and ask researchers or everybody to come up or to describe the data set, ideally visually. So these researchers go off, build all kinds of visualization tools and detectors and things like that to understand what's going on in the data. This was one of the visualizations, and I don't want to bash this paper, but and pretty much every single submission that I reviewed had this problem. They didn't clean the data. Well, how can we tell? Well, maybe this is a little bit of a telling sign. Here we go. That destination port, the source port there of 80 is probably the destination port. If you actually follow the lines, you will see that the destination port for this guy is all kinds of high port numbers on the bottom there. So it's probably exactly one of those cases where the source and destinations are turned around. So we have to clean the data up. If we look at the next part in here, there's a port 70,000. Okay? I guess you get it. And then, if you look at all these source ports, they really, or these destination ports here, if I were to analyze this data set, I would find all kinds of anomalies and say, oh my god, there's traffic to these high port numbers, there's probably some malware active here, we gotta look at this. Well again, this is probably exactly the counterpart of that port 80 there, and we have to turn that stuff around. Now the challenge is, I tried to actually clean this data set up at some point, and I did a whole blog post about it. It's really hard to figure out when you have to turn something around if you just have the raw network flows. Because you don't see which side sent the SYN packet and which sent the SYNAC and so on. It's a really hard problem, but we have to try to account for that. If we don't, we find all kinds of anomalies in this data set. And believe me, these researchers found all kinds of stuff. Among them, attacks on port 0, which is ICMP traffic, right? But these guys didn't know. They didn't have the domain knowledge. All right. Assume we have clean data. We're going to now engineer distance functions. We have to define, if I have two records, how far away from each other do we want to plot them on the graph? Are they going to be really far from each other, or are they going to be close to each other? So they basically define sort of the similarity between the different records. Well, you need to have domain-specific similarity functions. You have to take into account, this is a URL, for example. It's not just a random string. There's structure in there. If you have a host name, there's different parts to it, right? If you have port numbers, again, they're not just integers. Treat them as categorical data. Bind them together. Similar things need to go together. And then usernames are probably just categorical. Don't treat them as strings per se. On the right-hand side, I tried to, it's a very simple and maybe a little convoluted example here, but it hopefully shows that if you're clustering this traffic, and on the x-axis you have the port number, and the y-axis you have the number of bytes transmitted, well, just because that is port 443 up there, it doesn't mean it's an outlier, just because it's in the top right there, right? I couldn't use this, the distance doesn't make any sense in here, right? I can use this graph for making other statements that I see a lot more traffic being transmitted on HTTPS than on the other protocols, but I can't really say anything about clusters per se. So then, the next challenge, once we have good distance functions, and you should do some research on that, it's actually not that easy, but quite interesting, we have to figure out what clustering algorithm to use. There's a number of them out there. This is not all of it, there's just a few. On the right-hand side, you see a little bit of a visualization on different clustering algorithms are the color in here, and some of them are doing much better to actually match the structure of the data versus others that you see there's a sort of a disagreement between the structure itself and the coloring. It's probably pretty apparent. But when you're choosing the algorithms, you have to figure out what's the dimensionality of your data. Often I have pretty high dimensional data, a lot of columns in my data. And a lot of algorithms don't deal well with that. So I have to do something like PCAs, that are like basically reducing the number of columns, but I'm losing information that way. So is that still going to work? Then the shape of your data matters as well, because certain algorithms, they get a little upset when you're giving them certain shapes of data. They might find a local minimum where they're going to get stuck and things like that. So you have to take that into account. Often you have to know how the algorithm intrinsically really works. TSNE up here is a very interesting algorithm that's basically a multidimensional projection from high-dimensional spaces into a two-dimensional space. Super interesting, creates incredible results. These are actually TSNE visualizations here. But you have to know the intrinsic workings of this thing to really get the right results. And then often it's also, do these algorithms converge to something? And what's the speed of running this stuff? I don't have all year to run an algorithm on my huge data set to come up with a result. Sometimes I want to do this in almost real time to classify or cluster things. So that's where you see that you probably want to have a data scientist on staff. So here, I want to show you what happens if you don't understand your algorithm. What you see here is the same data set that I put into this TSNE algorithm, and the first, on the left-hand side, is I just downloaded the library, ran the data on it, and visualized the output. And what you see here, these are just machines on the network, the individual dots. If you look at this, and I would ask you, do you see any specific clusters in here? Or like, does the data separate in certain ways? You could say maybe, right? There's a bottom part there is maybe something that's a bit different. And you could come up with maybe some clusters in here, but it's not really clear. But then you go in and you discover, oh, there's these two parameters in this algorithm. There's an epsilon and a perplexity. You're like, let's see what happens if I change it. So I change the epsilon to 19, right? I crank it up, I run the algorithm again, and poof, I have 3 clusters in here. It's pretty nice separation, right? I have 3 different types of machines, it seems. And I'm like, oh, that's great. Maybe we can tune the other parameter too. Maybe we see even better results. So you start tuning these things and turning these knobs, and on the right-hand side, completely random. So if we actually put some ground truth on top of this, I'm not sure if you can see the colors here. If you advance it. Yeah. So here, this is the ground truth, right? Like, I'm overlaying what I already know about these machines. There's 2 clusters in here of data. There's the blues and the orange ones. In the middle one, we thought we had 3 clusters, but really the data set itself only has 2. So you see what happens if you don't understand what the algorithm does and if you don't understand how to tune these parameters. Here's another example that just probably drives the point home quite a bit if we highlight sort of the outlier there on the bottom right, where you can see we think that that bottom right little node is actually part of the cluster on the right-hand side there, right? And that can get really dangerous when you're starting to make decisions based on this. You don't know, like, you don't know those colors up front. That's what you're trying to discover. I'm giving it as a sort of showing what's going on here. All right, now we can assume we had clean data, we had the right algorithm, we had the right parameters set, but then you get an output and you have to interpret this stuff. Well, what are these clusters? Is this a web server, an email server, a DNS server? I don't know. I need to be able to introspect this stuff and look into it. How do you do that? Are these clusters good or bad? I don't know. What's anomalous in here? Maybe I can do something over time to find anomalies. And how do you find compromised machines in here? Right? It's not that easy. Okay, so that was the unsupervised case. Now, I want to take you through a last example where instead of using sort of traditional supervised and unsupervised learning that everybody's talking about, I want to bring back a very old concept of belief networks. People have used them 2 decades ago, kind of dismissed them. They're like, it's too complicated and it's not really going to cover everything, this and that. But I think there's actually some really, really interesting stuff we can do with them. And I see some startups that are starting to use these belief networks very, 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 in very interesting ways, and they get really good results. What we're going to play with here is a Bayesian belief network. What that means is, on the right-hand side, you see the textbook example. Assume we have a lawn. And I want to know, the question I want to ask in the end is, well, what's the probability that it's raining given that my lawn is wet? And what I can observe is whether the lawn is wet, I can go and test it. I can observe whether the sprinkler is running. And I can observe whether it's raining or not, right? And what I do is, I basically come up with this little graph, this dependency graph, and say, okay, I can go out and look at historic data. What's the likelihood that it's raining? And I can say, well, 20% of the time it rains in this area. I can then look at the likelihood that the sprinkler is on. And the sprinkler, it's kind of dependent on whether it's raining, right? I'm not going to run the sprinkler when it's raining. So that's a very low probability. But when it's not raining, I actually turn the sprinkler on. So I capture these probabilities as well. And then I can go and measure when the lawn is wet, and based on whether the sprinkler is on and whether it's raining. So I built these sort of joint probability tables. And by doing that, I come up with these different probabilities in this network. And then what I can use Bayes' theorem, which is too much math to go through here, but it's this formula on the bottom there for those who are interested, where I can then compute the probability that, given that it's raining, that my lawn is actually wet. And what we're going to do is we're going to apply this to network security now. All right? So let's go through this example here. What we want to do, I want to detect whether a device on my network is compromised. And to do that, I'm going to define behaviors that I can observe that are reducing my uncertainty of whether my device is compromised. So things I can observe, some facts I can observe. I listed a bunch of them. This is a toy example. Don't try this at home. But maybe expand on this and come up with a good model for it. But so I can observe all kinds of things, right? I can see if I have encrypted port 23 traffic. Why would that be weird? Well, encrypted DNS, telnet, that's often an interesting sign, right? Telnet is generally plain text. So that might be a sign that the machine is compromised. It's not always the case, right? Some people run encrypted stuff over 23 and it's totally fine. There's all kinds of other factors I can look at. Then what we do, one of the problems is that if we now went ahead and built this crazy belief network and started doing all these probabilities across all these different facts, it would explode very quickly. It's an exponential problem. I have to compute all kinds of stuff, and it's not going to help us much. So the trick here is we're going to introduce grouping nodes. These nodes are basically other probabilistic nodes, other observations, but they group together these different themes here a little bit. Let's look at the bottom left one, that the host is tunneling data. Well, I can define all kinds of observable factors to determine whether something is tunneling data. In this case, I just looked at a very simple thing, a protocol mismatch, or maybe that encrypted traffic on port 23. They could be indicators for tunneling traffic. There's all kinds of other stuff, right? You can look at DNS things and ICMP stuff, blah, blah, blah. Keeping it simple here. This model you can extend out much more, just to give you an idea of how this works. So you group these things, and then what you do is you introduce the dependencies between these things. The white arrows and the green arrows here are the obvious ones, right? Like, obviously the device is compromised. It's going to depend on whether I see anomalous network behavior or tunneling data. I have a hit on my threat intelligence feeds and so on. And then the individual observations can then lead into these other grouping nodes. But then I can also have dependencies between the different observations, right? Some of these are not independent. If I see that a machine shows up with a new operating system, that could actually be because the machine was just updated to a new operating system, right? So these two things kind of have something to do with each other. So once you have this whole graph built, what you do then is you go and you talk to experts. I've taken a little excerpt from the bottom left of the graph. I'm just focusing on this for the example here. I have these three nodes, right? I can ask an expert, what's the probability that I have a protocol mismatch on the network? And they give me, it's very low. It's like 0.01%. And I ask them for all these nodes to get this expert knowledge. Then I continue, and I can do conditional probabilities. I can say, well, you know, because these things are related, I can say, what's the probability that I have tunneling going on? Or if I have seen encrypted traffic, what's the probability I have tunneling going on? And there's some, in this formula, I see some of the terms I already discovered, I already asked my expert, and there's new ones I can add more knowledge to. And then I can go and do the joint probabilities over this stuff, and I get even more information. And you see what we're doing is we're asking experts pretty interesting questions that they can answer in general. We're not answering them with historic data. And so then, when we're looking at is the device compromised, well, we're taking the joint conditional probabilities over all of this stuff, and we're golden. So what does that mean now? So we built this network with the probabilities, right, from an expert. And then we observe what's going on out there. So we might see that we have a new OS showing up, the machine didn't get updated, and it's open port 53. And I have a probability that this machine is having anomalous traffic of 0.3, so 30% sure that it's anomalous traffic. By these new inputs, that jacks it up to 0.5, right? The network updates itself, and then going down to 0.1, and then if we continue computation, we get this to 70% compromise now. So this network updates itself with these formulas, basically. Now, to make this even more solid, what we are doing, we can now ask the experts all kinds of questions across this whole network that we have. And these questions actually make sense to it. What's the probability that the device is compromised, and I have a highly suspicious network behavior, and nothing on the threat intelligence feed? As an expert, you can answer that. You can say, well, you know, that's kind of weird. It probably doesn't show, that 30% of the time it doesn't help. Now you do this with 100 experts, 1,000 questions, and you get a pretty solid network that explains what's going on. Now the benefit of this stuff is, it's an iterative process. You have to keep doing this, right? We can actually verify what this thing learned. I can read out the probabilities and see exactly what this thing learned. I can extract the knowledge from it. And you can answer all kinds of questions. I can, for example, answer, what's the most determining factor for understanding whether a device is compromised or not? Which of the different inputs do I have to look at? And do I have the data for that? If I don't have the data, I might invest in getting that data. There's some disadvantages, and it's kind of hard to do sometimes. I also want a big shout out to my friend Chris at Response Software that helped me building this whole example and like entertaining all of my questions. So thank you, Chris. All right, so in summary, what did we just look at? Start with use cases, not algorithms. The algorithms are secondary. Once you have the use case defined, you will find out what algorithms to use. Often it's simple statistics. I just talked to an old colleague of mine, and we just talked about, oh my God, everybody using machine learning for finding anomalies. It's so simple to just write some rules and use simple statistics. Do some counts, some distinct counts and stuff. ML is barely ever the solution. As I just said, statistics often works. Use ensemble of algorithms, so multiple algorithms at the same time that they augment each other and sort of cancel out each other's problems. Teach the algorithms to ask for input. If the algorithm, if you know it's acting on a decision boundary where it's not sure, rather than making the decision whether it's left or right, ask an expert for input. Make sure this thing keeps up with change and so on and so on. And with that, as I said earlier, algorithms are getting smarter, but experts are more important. You all will still have a job tomorrow. Understand your data and your algorithms and your data science process. And history is not a predictor, it's knowledge is. Be careful. These belief networks, don't use historic data to train them. Because as we talked earlier, data is bias. I want to train these systems with expert knowledge, not with historical data. And with that, I think we're right on time. Thank you very much. Appreciate it.